tomorrow.
Yes.
I'm gonna work like every
Sports
single day.
fans, let's talk about what you should have from the Lim Lab.
Sports fans?
It's a phrase.
Ladies and gentlemen, cowboys and Indians.
Cowboys and Indians.
What you just said. That's why
Is it?
Yeah, mostly for you.
Okay.
All right. On the back side, on page 4, you want to calculate how much force the engines have to produce a given acceleration.
This was too easy.
Okay, so here's how you can check that you got this right. Basically, what I'm asking you to find is the applied force to make this acceleration happen. Okay? So if you work backwards and say, okay, here's the land, here's this applied force, which is what you, let's say you have an answer of 8,000 newtons, okay? Let's say you think that's the applied force that has to happen to make this acceleration happen. Take the 8,000 newtons, call that your force applied, add it to a negative 8350, right? Get the net force, divide that by the mass, see if you get the acceleration that I want. If you do, you did it right. If you don't, it's wrong. Now, let's look at just ballpark answers on that first one. How much force must the engines produce to get a vertical acceleration of negative 1.1? So, I don't want this, I'm not saying when you have this negative acceleration of negative 1.1, I'm not saying the ship is going down, I'm not saying the ship is going up. All I'm saying is that this is the acceleration that I want. So look, since I want a negative acceleration, does my applied force have to be bigger or smaller than negative 8350? Smaller. Okay? So right away, just because right away, as soon as I know I want that negative acceleration, I know my applied force, there's two things about that applied force. I know it has to be a positive number, because I'm not going to flip this limb over and fire the engines and make it go down. Okay, so neither of your answers on those last two questions should be negative, because if you have negative numbers, you're saying, oh, we've taken the limb, we flipped it upside down, and I'm going to fire the engines that way. Bad. Okay, that will get you fired from NASA that faster than about anything. So, when you look at that negative acceleration, your answer should be positive and less than 8350. If you want a positive acceleration, your answer has to be bigger than 8350, and again, it has to be positive. On that velocity time graph, there's a whole bunch of things that I want on that velocity time graph. I want if the net force is positive, if the net force is negative, if it's speeding up, or if it's slowing down.
Yo, what is that? Where is that at?
It's literally right here.
I mean, yeah, you.
It says
But how do you determine
right here.
it? You could have put it right above the graph if you're being
That probably would
honest.
have been a little easier off directions wise.
We had to make a velocity time graph.
I said, use this one. Yes?
How do you determine if the force, the net force is positive or negative?
Okay. So, Maddie has a legitimate question, unlike Hunter's.
Your directions were bad.
Oh, they are not!
Here, let's put the question to the last problem at the beginning. How am I
Use
supposed
the
to remember?
velocity time graph on the back, complete the following.
Okay, by the time I got to the back, I did not realize that was...
He just thought it was a pretty picture that you drew him.
I honestly had no
You should have a little
clue what
quiz to
the graph
refer
was.
back to instructions
I
on
swear, I have
page 3.
zero clue what the graph was.
I swear. You should read. Okay. Anyway, so here's the deal. At the end of the day, net force equals two things. Okay? It equals two things. It equals either the sum of all of the forces. It also always equals mass times acceleration. Okay? That's it. Two things force net always equals. So look, if you have a negative net force, what sign does the acceleration have to have?
Negative.
Negative. Which is also the slope of your
Mine.
velocity time graph. So anywhere there's a negative slope, guess what? You have negative net force.
Ah, that's what I did.
That's it.
That's it. There's only one of two things. Either it's speeding up, or no, either has a negative acceleration and a negative net force, or a positive acceleration and a positive net force.
Or there is no net force.
One of three things.
But then the velocity time graph is going to be
Are these two flat ones?
a horizontal line.
This one's, yeah, they're both positive.
Yeah.
You just kind of splitting up.
Okay.
Reach
Oh,
out the
you're
phone.
distressed.
Any other questions on the Lim Lab?
Positive, 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 negative.
Going once,
Positive.
twice.
I'm not that
So,
here.
so get that hand in action. Got it. All right. Okay. So y'all have used the stapler before, right? It's kind of cool. Let it go. There we go. Okay. So let's look at the physics involved in this. This is technically what's known as an Atwood machine. An Atwood machine is a system of either one or two pulleys and just weights that are acting in opposite directions. So let's start with the basics. So when I let go of it, does it accelerate? Yes. So that means the net force does not equal 0. Okay, so right away I know there's an acceleration. I know there's a net force that does not equal 0. So let's look at this. What's making it accelerate?
Nothing apparently.
What's making it accelerate?
That's force.
A force created by
Gravity.
gravity. So if gravity is causing the acceleration, is the acceleration then negative 9.8 meters per second squared?
No.
No. Because if I take even an eraser, right, and if I just drop the eraser,
It's going to beat it.
yeah, the acceleration on the eraser is a lot more. Now, obviously, if I do this and I shut off gravity,
That was at perfect height for him to slide the paper in.
there was, okay? Now, if I could shut off gravity at this instant and let go of it, what would it do? What did you say? Yeah, it just, there wouldn't be any force acting on it. So therefore, inertia says, hey, it's just going to remain at rest. So let's focus on this 500 gram mass. So when I let go of it, I know the mass of this is 500 grams. So when I let go of it, it begins to fall in that direction. So is the mass of the stapler bigger or smaller than 500 grams? Smaller. Now, do you think there's a big difference between the two of them?
No. It's going very, very slow.
Is your name Ellie?
I didn't hear you say my name.
Oh,
He never said it.
I did.
No, I don't think
I did.
No,
I did.
Rewind the tape.
Okay, Ellie, is the difference between these two big or small?
It's small.
Okay, because if the mass was, if the difference in masses was bigger, what would happen?
It accelerates faster.
Accelerate faster. Okay. Because if I just, if I put like an elephant on this side and the stapler over here, let go of it, whoop,
I think
okay?
the string would actually break.
Yeah, but stay with it still. Okay. So here's what we know. It accelerates towards the bigger mass, right? We have a small difference in mass, and we have a net force that is not equal to 0. Now, when I let go of it, let's say I've got it like this. This is 500 gram mass. 500 grams is how many kilograms? Half. 0.5 kilograms times 9.8 meters per second squared gives me 4.9 newtons. So if I were to just cut the string at this point, okay, if I were to just cut the string, how much downward force would be acting on the 500 gram mass?
No.
0.5 times 9.8.
Otherwise known as
Gravitational force.
Gravitational.
4.9 newtons, right?
Wait.
Why not 9.8?
Yes?
Yeah.
Okay. So if I just cut the string, I got a downward force, if you want to define this direction as being negative, that was a negative 4.9 newtons. I take a negative 4.9 newtons, which is now my net force because there's nothing else acting on it, right? If I take a negative 4.9 newtons and divide that by 0.5 kilograms, oddly enough, I get,
So you're dividing again?
if I take negative 4.9 newtons and divide that by 0.5 kilograms,
9.8 negative.
yeah, I get negative 9.8 meters per second squared.
Yep.
Because the only force acting on it is going to be gravity. That is my net force. There is no opposing force because the stapler isn't part of the system. Boom, I cut it. Now, if I were to cut the string here, the force acting on the stapler is going to be a little bit less than 4.9. Okay? But the mass is a little bit less, but I'm still going to end up with the exact same acceleration. So, you can actually look at this in terms of like an applied force and an opposing force. So, to make this simple, we're going to make the force acting on the bigger object the applied force. So, because it's got to drag the stapler with it, we're going to make the stapler the opposing force. Now, here's the whole kicker. So, if this is my applied force, and let's say I make this positive, okay, it doesn't make any difference, let's just make it positive. So let's say this is 4.9 newtons. And let's say this thing, we're going to make this the applied force, 4.9 newtons. So let's say the opposing force over here, if I were to find the weight of the stapler, let's say is 4.6 newtons. So if that's 4.9, and this is 4.6, what would be my net force? 0.3, right? Because I got a 4.9 Newton force going this way. I got a 0.3 Newton, or a 4.6 Newton force opposing it. So the difference between those two is going to be 0.3. Now, but here's the kicker. When I let go of it, is that 0.3 newtons just accelerating the 500 gram mass? No. What else is it accelerating? The stapler. So this is the key thing at the end. Listen to me. This is the key thing at the end. When you get that acceleration, you always divide by the total mass of the system, no matter where that mass is. So when I let go of this thing, that net force isn't just accelerating the 500 gram mass. It isn't just accelerating the stapler. Both of them are being accelerated. So at the end of the day, listen to me, on a problem like this, or any kind of problem like this, at the end of the day, you always, always, always divide by the total mass of the system. Because the whole mass is being accelerated. So if you think about it, it's like taking a 0.3 Newton force and making that 0.3 Newton force accelerate both of these together. Okay? Because that's going to be the net acceleration of it. So whatever the difference is between the weights of the two systems, that's your net force. Then that net force is going to accelerate this whole system together. That's why you always, at the end, divide by the total mass. No exceptions whatsoever. None. Zero. Zip. Okay? None. Zero. Zip. Okay. So,
Any problem? Ever?
ever. Always divide by the total mass. All right. So here's what we've
Didn't do
got.
that yesterday.
So, we're just going to generically call this M1, and we'll make this M2. Now we're going to let M1, for the sake of argument, be greater than M2. Okay? So here's the setup. I don't care what the masses are. Okay? I don't care. It doesn't matter. I would just want to find a generic way that I can work any problem like this. So this one is going to accelerate in this direction because M1 is bigger than M2. So we're going to call this fat. Okay? So whatever the weight of the bigger object is, we're just going to say, okay, this is the applied force that's going to make this system accelerate. So to get that, we're going to take m times g. Whatever the mass is times whatever the gravitational acceleration is. For the sake of argument, we're going to make that positive. If you want to make it negative, fine, make it negative. I always make it positive because that's the direction that it's going to go. Okay? Doesn't make any difference. Now, we're going to make this my phi, because gravity is dragging this thing down, and it's like it's working as an opposing force. So it's like you're trying to be cool on a date, but you've got to drag along your nerdy little brother. This is an opposing force to you being cool. So this is also going to be M2G. So we're going to make this M1G. We're going to make this M2G, right? Now, for the sake of argument, if I'm going to make that positive, what side do you think I want this to be? Negative. Okay? If you want to make that negative, fine. Make that then positive. They just have to be in opposite directions because that's the direction they're moving. It doesn't make any difference which one you make negative and which one you make positive. Literally. Doesn't matter. Okay? Doesn't matter. Now, so net force always equals the sum of the forces. So what are my two forces? Applied and my opposing. So my net force is going to equal my FAP, which is going to be M1G minus M2G. Okay, it's going to be the difference between those two. Now, what can I do to make this a little bit simpler? Hum. I've got M1G minus M2G.
Can you divide it out by G?
Why not suddenly divide? You can factor it out. Okay? So my net force I can write as G times M1 minus M2. Right? So this by itself is going to give me the value of my net force. Now, let's talk about this. What if M1 and M2 are the exact same mass? What will my net force be? Zero. Because my applied force is the same as my opposing force, and guess what? It's never going to accelerate. Okay? So, look at this. The bigger the difference between M1 and M2, what's going to happen to my net force? No. The bigger the difference between M1 and M2. I've got an elephant on one side and a mouse on the other.
The bigger your force is.
Yeah, I'm going to have a huge net force the bigger the difference is between those two values. Okay, so here's what we've got. Here's my pull weight. Here's M1. Here's M2. This thing is going to go in this direction. So here's what I've got right now. My net force is going to be G times M1 minus M2. Now, what else does my net force equal?
Mass times acceleration.
But which mass do I use?
Both.
Oh, both! Oh! So now my net force also equals M1 plus M2 times A, right? Net force is mass times acceleration. So here's what I've got. I've got M1 plus M2 times A equaling G times M1 minus M2. So what can I do to get A by itself? Meet. What can I do to get A by itself? Do not make this difficult. I want to get A by itself.
Divide M1 plus M2.
Yeah.
Good.
Divide M1 plus, there you go. There's my value for acceleration. Now, let's play the what if game. Okay?
Okay, what if? Joke, man. It's the joke.
What if M1 and M2 are the exact same value? What's my acceleration going to be?
0.
0. The system won't accelerate because there will be no net force. Okay? Now, let's go to the setup over there. What if I just cut the string and just focus on M1? M2 at that point is no longer part of the system. M2 goes to 0. So now, I've got M1 minus M2 divided by M1 plus M2. If I cut the string, my M2s are what? Gone. So now that I'm left with M1 over M1, which is going to be 1. 1 times g gets me, and the acceleration of the system is 9.8 meters per second squared.
Wait, wouldn't it be 9.8 times mass?
But if it's the same mass, whatever the mass is, if it's 1 kilogram divided by 1 kilogram, or an elephant divided by an elephant, it's still going to cancel out to 1.
This is just for pulleys, right?
Or, yeah.
That's
in this
just like,
situation.
isn't that just like saying, say we cut in 1? Is that just like saying you're dropping about 500 kilograms?
It is, but here's my point. So gravity is still acting on the system, but there's no opposing force, so the acceleration just becomes 9.8 meters per second squared. And the beauty of this is, it's no matter what the mass is. And this harkens back to this whole idea. Whether I drop an elephant or a marble doesn't make any difference. As if I cut the string on the other side, my acceleration is
So there's
always
no
going to be
opposing force.
9.8 meters per second squared.
All right, I think I understand.
Okay? Got it?
Thanks.
Good. Okay. So, stop that. Let me hand out the lab. So, let me kind of take you to, there's 2 main parts to this lab. The first part, in terms of the collecting the data, is fairly simple. So, you're going to take a 500 gram mass, okay? 500 grams.
Check.
And you can use a piece of string, or you can just hook it directly up to the 10 Newton scale. Doesn't matter. I like using a piece of string. And you can hook that up, and you're going to make sure that you re-zero the scale, okay? And you're going to hook this up, and you're going to be like this, okay? So there's a couple of things that you're going to do. You're going to accelerate it upward, you're going to accelerate it downward, and then you're going to move it up at a constant velocity, down at a constant velocity. Now, here's the deal.
Is that Newton scale maxed out? I can't tell.
It's a 10 Newton scale. I'm only holding up a 500 gram mass.
Okay, did you zero it though?
So what's that?
To be fair, it is really hard to
Oh.
tell where it is at.
I can't see it.
Okay,
Is that
here's
250?
10 Newtons all the way down
Yes,
here.
I get
Is that 2.5
or if it doesn't say 4.9, your instruments need to go back.
It does say 4.9.
Are we sure? So why do we even measure it out?
Because we know.
Because science.
Okay, so here's the deal. Is the spring scale reading one of 3 forces? Is it measuring the applied force, the opposing force, or the net force?
Applied
Applied
force.
force.
Net force.
Net force.
Net force?
Yeah.
Let me think about it.
Go charts. Net force.
Okay,
If you push up, it's going
Oh no, it's FAP.
No.
Okay.
I don't know. What's the applied force?
I don't know.
Like,
Well, let's look.
oh, it's the opposing. It's the opposing. Because you're holding it up. Because you're holding it up using applied force, and it's going down using
Words are hard. Words are hard.
Okay.
It's on the sheet.
It's the very
Underlined, bolded,
See it
all that fun stuff.
Yeah.
Yeah, if you said
No.
net force or opposing force, you probably really don't.
You're lifting it up. That is the applied force.
I realize that.
So
That's-
it is going down with opposing force.
Okay.
Are we
Right
we have
now-
to push?
Right now, what's the acceleration of the system?
0.
Therefore, the net force is,
Zero.
so
how can it be
So
net?
right away, I know I can't be reading the
Net.
net force. Okay? Now, let me pose this question. And don't do this, people, you might get arrested. But let's say that for whatever reason you walk into a nice hotel wearing a large trench coat and you happen to have a bathroom scale inside the trench coat. Okay? Like I said, don't do this. This is a pure thought experiment. Okay? So you walk into the elevator, hopefully alone, and you take the bathroom scale and you set it down. So you're standing on the bathroom scale in the elevator. The elevator is not moving. Okay? And let's say that you look down and the reading on the scale is 150 pounds. Okay? 150 pounds. Look down, solid. You're not moving, 150 pounds. Now you want to go up to the 10th floor, so you press the 10th. So as soon as that elevator begins to accelerate you upward, what's going to happen to the reading on the scale? One of three things. One of three things. It's either going to get bigger than 150, maybe go up to 160. It's going to stay at 150 because gravity hasn't changed. Or it's going to become less.
You just taught me that it is force applied. Because it's going to get bigger. Because
Yes.
the applied force is going up. And it's getting bigger because there's more applied force.
Okay, because if you're going to accelerate upward, the applied force has to be greater than the opposing force of gravity so that you end up with a positive net force. Okay? So if you've ever ridden an elevator, okay, and you press the up button, you kind of feel a little heavy. Okay, it's like, whoa, okay, kind of get that feeling going. Because it's a highly technical term, but it's true. That whoa just means that your body has mass, specifically your stomach in general, and it wants to remain at rest. And so what the scale is measuring is the applied force acting on you. Okay? So let's say that the scale reads 160. It would normally be 150. So what would be the net force acting on you? 10 pounds. Okay, if you were in newtons, it would be in newtons. Okay? So if you're going to accelerate upward, your applied force has to be greater than your gravitational pull. Okay. Now, once you start moving at constant velocity, you look down on the scale, what's it going to read? Back to 150 because you're still moving, but you're moving at a constant velocity. Now, you get up to the 10th floor and you go, I better get out of here, they've called security. So, you press the downward button, going back down to the main level. So you look down on the scale, what's the reading on the scale going to be? Greater than 150, less than 150, or equal to 150, or will it be 0 because you're going to be in a state of weightlessness because you're falling?
You're gonna weigh what?
Less.
How would you weigh
Are you saying
zero?
the elevator's failing? Like it's just going
No,
down?
I'm just saying, what's the possibilities?
I mean, if it failed,
If it failed,
What are the
if the
chances?
cable
Zero.
will absolutely snap,
it could be 0.
then it would be 0. But assuming that it doesn't fail,
Yeah.
you're still going to, the elevator is still there, right?
Worst way to go.
But it's going to allow you to accelerate downwards, so therefore your applied force has to be less than your gravitational force, therefore you accelerate downward, you kind of go, you're going to get that feeling
We
going.
have a serious question.
Okay,
If an elevator fails and you jump at the last second,
you're still screwed.
UI.
Because assuming that it falls any length of distance,
Okay, let's say
you're
we're
going to
5
have
stories.
you're going to have so much kinetic energy at the bottom, and you're going to be going so fast, whether you jump or not. I mean, it's not going to make any
You
difference.
think
Is
the
there
top
anyone
would
not
collapse?
die?
Oh yeah, I mean you're
So you're like jumping into like something hitting you in the head.
yeah, I mean the whole thing is just going to go. I mean, it's just going to be an absolute catastrophic train wreck, no matter what you do.
Look can we tell us
Okay.
a smile on his face?
Oh, that's something completely different.
Who does that?
Okay.
Who are those people?
All right. So yeah, it was one of the problems. Okay. So on the front page, here's all what you want to do. You're going to have 4 different situations. Up at a constant velocity, down at a constant velocity, accelerating upward, accelerating downward. So it doesn't have to be a big acceleration. Don't go, we can't read it. You don't have to accelerate it a whole lot, okay? And if you really want to get fancy, accelerate it, record it with your phone, play it backwards, and get the reading that way if you really want to get technical about the whole deal. Then, basically, the rest of page 1 and all of page 2 are questions about different scenarios involving that. Now, page 3 is the Atwood machine. So what you're going to do is you take a setup like this. You got a single pulley, roughly about 1 meter of string. It doesn't have to be that much. You want to tie a couple of loops at the end, or you can just tie the weights to it. It doesn't make any difference. Okay? I'm kind of a fan of loops. So we got a couple of loops. Here we go, loop. Okay. So we got this action going. Then you need a 200-gram mass on one side, like such, and a 200-gram mass on the other, like such. Okay? Now, at this point, what's going to be the acceleration of the system? 0. Why? Well, the net force is just going to be 0. Gravity's pulling down on both of them, right? That isn't the issue. Gravity's pulling down. There's all sorts of forces involved. You know, I got to hold this thing wants to bend up, there's gravity pulling down on the whole system, you got the table involved, but all of the forces added together are just going to add up to equal to 0. So then what you're going to do is you're going to take a 20-gram mass, and you're going to connect that to one side. So you can hook that up on one side, and there's a couple ways that you can do it like monkeys and hook it that way. You can hook it up from the same common loop, whatever. Okay. Now when I let go of it, we get an acceleration. So which one is the applied force and which one is the opposing force? The 220 or the 200? Which one is the applied force? The 220. We're going to make the bigger one the applied force. And it says so in the instructions. Okay? It says so in the instructions. Now, what you're going to do is you're going to calculate two different accelerations. One being a theoretical acceleration using that equation that's up on the board. And you're also going to calculate an experimental acceleration. Now, when I let go of this, what are some things that I could measure to determine the acceleration? What's one thing that I could easily measure when I let go of that?
The time.
I could measure time. Okay? What else could I measure?
Distance.
I could measure distance. Now, if I'm clever, which you all are, what are you going to let the initial velocity of the system be?
0.
0. Oh, let's talk about that. So, let's move back over here.
Oh, because you're holding on to it.
So, here's the deal. You know this equation that x equals 1/2 at squared plus v naught time. True? If we're starting from rest, what's going to happen to this whole thing? Yeah, I don't have to worry about all of that. X is going to be what? The distance that it's going to travel. A is going to be your acceleration. T is going to be your time. So we can measure the distance, and it doesn't make any difference which distance that you measure. If you want to put one all the way down on the floor and then have it go up a certain distance, that's fine. If you want to measure how far the other one falls down, I don't care. But here's what you have to be very careful about, because there's a whole bunch of different ways you could measure this. Are you going to be measuring from the bottom of the weight? Are you going to be measuring from where the string connects to the top of the hook? Are you going to be measuring from the top of the weight? I don't care. It doesn't make me any difference. You just have to make sure that everybody's in the group knows exactly the point that you're using as that reference. Okay? I don't care. Now, let's look at this. We've got 2x to get acceleration over t squared is going to equal my acceleration. If you're clever, what do you think the easiest distance for x that you could use? And don't say 0. It's easier 1 than 1.
10.
No.
No.
2.
10 meters?
4.9.
I didn't know we were meters.
1/2,
4.9.
A half. Why?
because then it's just 1/t squared.
Yeah. So if you don't have to, but if I were doing this, I'd let the distance be a ½ meter, because then it's just 0.5 times 2, which is 1, and then I'm just taking the inverse of my times squared.
So you got 2x divided by t squared.
And then you get the acceleration.
Yeah.
Which is
So this is
Which
going
would
to
be
be
4.9
your this is
squared.
going to be your experimental. This is going to be your experimental acceleration. The previous one is going to get you your theoretical acceleration, and so then you're basically going to compare the two of them. Okay. So this is actually what you get. The other one is like an absolute theoretical best case scenario. Now, if this lab is an absolute home run, if it goes south, it typically goes south because of errors in timing. Okay? So who's ever timing, you want at least 2 people timing this thing. Now, if there's a big discrepancy in the time, don't go, oh, we'll just take the average. Bad. No. Don't do that. If there's a big discrepancy in time, something went wrong. Okay? And literally, if this goes south, it's because of poor timing. Now, if you're a timer, if you're going to use whatever distance you're going to use, I don't care. But here's what you don't want to do. Don't stop, don't have somebody grab the weights at that point. You want it moving when it crosses that point and then stop it. Okay? Because otherwise, you're including that acceleration at the end where you're making it stop. Don't. So, let it fall, stop the timer, then stop the weights. Okay? Don't try and stop the weights at that distance. Otherwise, bad things are going to happen and your data will be all jacked up. So, what you're going to do is that you've got 5 trials with the 200 and the 220. Take the average of the time, that way you only have to do this calculation once. I don't want you to find 5 different accelerations. I just want you to take the average of the times and then find it that way. Now, everybody's numbers are going to be different. Make sure you show your calculation. Now, after you get done with that, then you're going to go back to the same system, and now you're going to put an additional 20 grams on here. So now, let's look at what's going to happen. So, what do you think is going to happen to the acceleration of the system?
Oh, it's going to be bigger.
It's going to be bigger. Now, why is it going to be bigger? Greater amount of net force. Okay, let's talk about that answer. So, there is going to be a greater amount of net force. But what have I also increased by adding the 20 grams? I've increased the mass of the system, so I've actually increased the, rhymes with inertia, the inertia. So I have added on the applied force side. Okay, I have created more applied force. Have I changed my opposing force? Opposing force is staying the same. I've made my applied force bigger, but I've also made the total mass of the system bigger. Okay? So, if you get a bigger acceleration, here's what I want you to look at. You have to realize, okay, hey, there's a bigger acceleration, but look at this. Just don't realize, well, there's a bigger acceleration just because there's a bigger net force. There is a bigger net force, don't get me wrong. But there's also more mass to accelerate. So basically what I want you to look at is that the increase in net force is more than enough to compensate for the increased inertia of the system by adding that 20 grams on there. So you should see a difference in the accelerations. Okay, so those are the 2 parts to the lab. What I would suggest is that get all of the data first and then start on the analysis with the questions. And remember, always assume that your lab partners are idiots. Don't trust any calculations that they do. Okay, so this is going to be due on Wednesday since we don't have class tomorrow. Okay? And if you haven't handed in that Lim Lab, I need it. All right, go. Lab freely.